Number 36, Chapter 8. What we have here is total yearly purchases in dollars versus income. Now, the income's also in dollars. The graph is showing it in thousands of dollars. So we have two quantitative variables. We have a we have a linear association. It's certainly not curved and it's not random. We don't have any outliers that we're going to worry about. Outliers that we worry about are over in this direction, out on the x-axis and away either above or below the pack. These really distort the slope of the line. But we don't have any of those. We have some outliers like here, a little bit above. That's okay. Weakens the correlation, but they are not problems in and of themselves. So, what is the linear regression equation for predicting total yearly purchase from income? Well, they give us all the information we need to do that. So let's start with A. The general formula is estimated output equals B sub 0, which is the starting point, the y-intercept, plus B sub 1 times whatever the independent variable is. So the estimated dependent variable equals B sub 0 plus B sub 1 times the independent variable. Now in this case, income is the independent variable and the dependent variable is total yearly purchases. So it's total yearly purchases versus income. So let's make B sub 1 first. B sub 1 equals R, we can put R over 1 or whatever, times the standard deviation of the dependent variable over the standard deviation of the independent variable. In this case, B sub 1 is going to equal 0.722 times the standard deviation of the total yearly purchases. That's the dependent variable. That's y. And that standard deviation is 253.62 divided by the standard deviation for the independent variables. That's income. And that standard deviation is right here, 16952.5. So let's double check our numbers. Correlation R, 0.722 times the standard deviation of the dependent variable of the response variable, which is total yearly purchases. It's the one on the y-axis, 253.62, divided by the standard deviation of the independent variable, in this case income. That standard deviation is 16952.5. So we will put this into our calculator. (253.62) and then divided by 16952.5. Now let me double check. 0.722 times 253.62 divided by 16952.5. I hit enter and I get B sub 1 is approximately equal to, that's what that little squiggly equals means, 0.0108. Now that's certainly pretty close. Okay, so now I can store this inside the calculator, and let me do that. I'm going to hit the store key, STO, and I hit the alpha key, and then I'm going to hit the math key with the letter A over it. You can see the little letter A, and I hit enter. And now this number has been stored inside the calculator. I'm going to put an arrow next to it, stored in A. So now I have B sub 1 in A, and I can call it up if I want to. Okay, B sub 0, which is the other number I have to calculate to make the model, equals y bar minus B sub 1 times x bar. So in this case, it's going to be B sub 0 equals the mean of the dependent variable minus the rate of change, B sub 1, times the mean of the independent variable. So in this case, b sub 0 is going to equal the mean of total yearly purchases. That's the response variable, the dependent variable. So that's going to be 572.52 minus 0.0108 times 50343.4. That is the mean of the independent variable of the income. Okay, so b sub 0 equals 572.52 minus. Now I can use, this was my last operation, and this answer is resident in memory, and I can hit second and then the negative key, and that puts answer on the screen. Oops. And then I'm going to put in times 50343.4. So let's double check our numbers. 572.5 minus 0.0108 times 50343.4. And I hit enter. So I get 28.732. And let's just, for the heck of it, let's store this number as well in case we want to call it back. I don't know if we will need to or not. So I'm going to hit the store key. I hit the alpha key. Now this time I want to use the letter B. I don't want to use A again. So the letter B is above the key that says apps. So I hit apps, and it's now the y-intercept is stored in B and the slope is in A. So estimated total yearly purchases, let's call it TYP in dollars, equals 28.73 plus 0.0108 times income, yearly income in dollars. Okay, so estimated total yearly purchases equals 28.73 plus 0.0108 times the yearly income in dollars. Now the graph says, the graph scale is in thousands of dollars, okay, but the units for the input clearly are dollars, since the mean is $50,000. It's not 50. All right, so that's A. We finally got our equation, and we got the constants stored in case we want to use them. All right, so let's go down. Let's go to B. Do the assumptions and conditions for regression appear to be met? I think we talked about this already. We've got two quantitative variables. They got units of dollars. Income is quantitative, units of dollars. Total yearly purchases is quantitative, units of dollars. We have an association that is linear, it's moderate, and it's positive. It doesn't really have terrible outliers. Again, bad outliers would be away from the pack on the x-axis and down on the y-axis or up on the x-axis. Such a point would pull the line of best fit towards it and really distort the model that we get from it. So we wouldn't want to use an association like that unless we did something about these points out up here or down here, away on the x-axis and either down or up. We say those points have leverage because they pull the slope towards them. We could have a similar point, like let's say way up here or something like that. Okay, we don't have any points like that. We have some points up here. These make the correlation weaker, but they do not distort the slope of the line. That's the thing we most care about, is this number right here, because this is the rate of change, and that's the most important part of this model. All right, so anyway, the assumptions and conditions are met. However, we don't have a picture of the residuals, so we do not have final confirmation that that indeed we can use correlation to describe this association. But with what we have so far, it does not rule it out. Okay, what is the predicted average total yearly purchases for someone with a yearly income of $20,000? Okay, estimated TYP in dollars is going to equal 28.73 plus 0.0108 times $20,000. Okay, so we can do it like that. A bunch of different ways to do it. Let's do it this way. Okay, so 28.73 plus 0.0108 times 20,000. So 244.73. So the estimated total yearly purchases of someone with an income of $20,000, which isn't, obviously it's not very much money, is about, the estimated amount is $244.73. Now, what about somebody who makes $80,000? Well, to make this easier, we can hit second and enter. The same command comes up and we can edit it. We can arrow up and then over. This is if we think we put the first command in, okay. Change the 2 to an 8 and hit enter. Okay, so the estimated total yearly purchases for $80,000, sub 80,000, equals $892.73. Okay, so all right, so D. What percent of the variability in total yearly purchases is accounted for by this model? Now, the percent of variation in general that's accounted for by the model is called R squared, which equals R squared, which is going to equal 0.722 squared, which is 0.52. Let's call it 0.52, approximately equal to 0.52. So R squared is the percent of variability in the response variable accounted for by the model. So in this case, 52% of the variability in total yearly purchases is accounted for by this model. 48% is not. It's reflected in the residuals and is accounted for by other variables. E. Is this model useful? Well, it explains about half of why there's of the variation in total yearly purchases. That's something. And it's a good thing to know, to have some kind of model so you get some kind of handle on the differences in yearly purchases by income. There's a big difference between somebody who makes $20,000 and somebody who makes $80,000. So it is useful on that basis as well. So, how is it useful? The model explains about half of the variation of total yearly purchases in dollars versus dollars of yearly income. That is useful. It allows comparison. The model allows comparison of different income levels. Okay, that'd be a good thing to know. That is it.